Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will use the comparison test to determine whether or not some improper integrals converge or diverge. Before we do that, there is a class of very simple functions for whom it is very easy to determine whether they converge or they diverge, and these functions are very simple, and we very often use them in the comparison test. So if we take any positive number and any real number p, if p is bigger than 1, then the integral from a to infinity of 1 over x to the p converges. And if p is less than or equal to 1, then the integral from a to infinity of 1 over x to the p diverges. So just to drive it home, or before I drive it home, the proof is a simple exercise. You just need to work out the integrals. So, for example, the integral from, let's say, 1 to infinity of 1 over x dx diverges, and the integral from 1 to x over x squared dx converges. And where does this come from? You can either work out these integrals just by hand. Those are easy integrals to work out, but this is a general principle which follows from the p-test. So for example, now it is, so from the p-test, for example, this integral converges, and this integral diverges, because a half is less than 1, so the integral diverges. Okay, so here we have a whole family of functions for whom we can decide fairly easily whether their improper integrals from a to infinity converge or diverge. And those functions, since they are so easy, we can use them in the comparison test to show whether or not other functions converge, or the improper integrals of other more complicated functions converge or diverge. Okay, let us take a look at an example. So, example. Determine if the following integral from 1 to infinity of cosine squared x over x squared plus 2x plus 2 dx converges or diverges. Okay, notice here we are not being asked to determine the value of this integral. In fact, this will be a rather difficult integral to determine its value of. But we can, using the comparison test, at least determine whether or not the integral converges or diverges. So let's try that. So for all values of x greater than 1, we know that the cosine squared of x is bigger than or equal to 0 and is less than or equal to 1. And also we've got x squared plus 2x plus 2 that is bigger or equal to x squared plus 2 plus 2. So if x is bigger or equal to 1, 2x is going to be bigger or equal to 2. But also this is strictly bigger, so x squared plus 4, that is bigger than x squared. So if we now rearrange this a little bit, everything here is positive. So if we divide both sides by it, what do we get? So we also have that x squared plus 2x plus 2 is going to be less than 1 over x squared. And also what can we then say about cosine squared x? X squared plus 2x plus 2. So just to drive it home, for all x that is bigger or equal to 1, this is going to be bigger or equal to 0. This is going to be bigger, is going to be less than or equal to 1 over x squared. So this part is less than 1 over x, and the cosine squared is less than 1. So we see here, for x greater than 1, we have this expression sandwiched in between 0 and this simpler expression. Okay, but we know something here. So by the p-test, the integral from 1 to infinity 1 over x squared dx converges. And therefore, by the comparison test, so since the bigger one, you see the bigger one converges by the comparison test, we have that the integral from not 0 to 1, from 1 to infinity of cosine squared x squared, what was it, plus 2x plus 2 dx also converges. We do not know what its value is, but we at least know that it converges, so this limit exists and is finite. And also, just to drive it home, what is the situation here? We've got, we're looking at the integral from 1 to infinity. What does the function that sends x to 1 over x squared look like? Looks something like that. And now we've got this funny oscillating function oscillating because we've got this cosine squared in here, but it is rather complicated, but it, for all values of x greater than 1, it lies below the function that sends x to 1 over x squared. So this integral, the integral of our complicated function, we don't know what that integral is, but we do know that it converges because this bigger integral exists and is finite. So therefore we know that this integral converges. That is it for this example. I will see you in the next one.